All right, let's talk more about this energy chapter here. So what we were saying before was, if you know how much energy a reaction will release, you can use that as a relationship to do conversions. And we're talking a lot about how, depending on whether the new bonds that are formed are more stable than the old bonds, we can determine if it's going to release energy or absorb energy. But this next section allows us to understand how, in the lab, if you have a reaction, you would physically go about setting up an experiment to measure the energy exchange that that reaction has with the surrounding. So to do that, you need a calorimeter. And a calorimeter is a device used to measure energy exchanges between system and surrounding. What's nice about a calorimeter is it is insulated. And so when you set up your calorimeter and you have an insulated container, so no heat will be exchanged with the surroundings. If you have two things reacting in the reaction and they are converting into some products, if that reaction releases energy, the energy will all stay inside the calorimeter. And so if you set that up with a thermometer, you can use a change in temperature to determine how much energy was released between the system and the surrounding. So that will give you the energy exchanged in units of degrees Celsius, right? So if you have the reaction starting at room temperature, you observe that the reaction caused the temperature to go up to 40 degrees Celsius, you can tell that you have some idea about the quantity of energy released, but it's expressed in a change in terms of a change in temperature. So that's not really an energy unit. For energy, we need units of calories or joules or kilojoules. So we need a relationship that will relate how much the temperature changes inside the calorimeter with how much energy is actually being exchanged. And that relationship is called specific heat. So inside the calorimeter, I would probably have a solvent, maybe like water. Because water's specific heat is known, and that is a relationship. The units for that are here. They're joules per gram of water per degree Celsius change for the water. That's a relationship. It tells me, depending on how many grams of water I have in here, plug that in here. Depending on how much the temperature changes, plug that in there. I can relate that to how many joules of energy that water must have absorbed or released, depending on whether the temperature went up or down. So specific heat is really nice. It's also known for lots of other substances, so I can do an experiment if I want. If I make a new substance, I want to know what's its specific heat. I could take a chunk of iron or something with a known specific heat. I could heat the iron up. I could put it in the water. I could see how much the temperature of the iron went down. And if I know how much the temperature changed, and how many grams of that iron I have, I know the specific heat of the iron. That tells me how many joules of energy the iron exchanged with whatever was surrounding it. So let's look at some examples here to illustrate this relationship. So for water, the specific heat is 4.184. That's the number of joules the water would absorb if I had 1 gram of it and the temperature of the water went up 1 degree Celsius. The heat capacity, though, is something that is not specific for the quantity of water I use. So this is heat capacity and specific heat are very similar. They both measure how much of an energy change there is depending on how much of a temperature change there is. But heat capacity is not standardized for a specific quantity like specific heat is. So if I take a cup of water versus a huge tub of water, they will have different heat capacity. Right? How much energy would it take to raise the temperature of a tiny cup of water by 1 degree. Not much, because I don't have a lot of water there. I just have to get, on average, the molecules moving faster. I have to transfer some energy into that to make it increase its temperature a little bit. If I have a huge quantity of water, though, it's going to take a lot more energy to put into that to make all the particles move faster, so that on average they're moving fast enough to increase the temperature by 1 degree. So heat capacity is different for every substance depending on the quantity of the substance you have. It's not as useful. Specific heat is a more useful number because specific heat tells me per gram of the substance how much energy is necessary. So the specific heat of water is the specific heat of water. The specific heat of water is always the same number, because if I have a gram of water, that liquid water always requires the same amount of energy to increase its temperature by 1 degree. So if I wanted to know, say, what's the heat capacity of a kilogram of water, how much energy is it going to take to raise the temperature of a kilogram of water by 1 degree, I would use the specific heat as a relationship. Right? This is a relationship. It's 1 unit. It's not the normal relationship we see, which is 1 unit per another unit. It's 1 unit per 2 units. It's still the same relationship, though. If I'm using it as a relationship, I use it to cancel units. It helps me realize how I need to plug things in to get the units to cancel appropriately. So if I want to know heat capacity, which has units of joules per Celsius, I'm looking for how many joules per Celsius this kilogram of water will have, or how many joules of energy are needed to increase that by 1 degree Celsius, that specific sample of water. And I have the specific heat, which is known to be 4.184 joules per gram per degree Celsius. I know that the only difference between the units I have in specific heat and heat capacity are the presence of those grams. So if I want joules per Celsius, I need to cancel the grams. So I would add a relationship, or multiply by that how many grams I have. If I have a kilogram, and I know the relationship between 1 kilogram is that it's equal to 10 to the 3rd grams, now everything here is canceling except the joules and the Celsius, and those are the units I want. So that's going to give me this number here. So that's just one relatively straightforward example of how you can use specific heat as a relationship. And the specific heat for many substances is listed in tables, including this table here, and there's also other tables where you can online where you can find that information if you need it in a relationship. I don't expect you to memorize specific heats. If you need one, it'll be there for you on the exam. You can use that as a relationship, or if you want, you can use the formula. So I know a lot of people aren't really comfortable yet with the conversion method. They don't feel confident about it. If you feel more confident about using a formula, the formula should also be on the formula sheet. So you're welcome to use that. If you want to use the formula, you plug in mass, you plug in specific heat, plug in a change in temperature. So that's the other key thing. It's not just what is the temperature, it's how much is the temperature change from where it started at the beginning of the process that caused that energy to be exchanged. And then Q is the heat exchange. That's the heat energy exchange. So since you have that formula, you could, as long as you're given any 3 out of these 4 quantities, you can solve for the other quantity. Same thing for heat capacity. If you know the heat capacity and the change in temperature, you can get the heat. Or if you know the quantity of heat and the heat capacity, you can figure out how much the temperature would change. Now that's pretty practical. You know, if you want to know, if you're going to do this reaction and it's going to release heat, you want to know how much is the temperature going to go up. Is it going to go up so much that my container will start exploding or melting or something? I want to be able to predict what the temperature change is going to be when I do a process. So here's an example we can use to illustrate that. So in this example, we want to calculate the amount of heat. So we're looking for Q. We're looking for kilojoules. So personally, I like the unit conversion method since I use it for everything. I'm used to using it. It works well for most things, and it also is nice because it allows me to focus on units. If I'm just plugging into a formula, I might calculate heat in joules. But if the question is asking me for kilojoules, but I think I've put it in kilojoules, but it's really in joules, I'm not getting the right number. Right? So the conversion method is nice because I set it up and I say, what units do I actually want? Then I can start to plug things in. I can end up with those units. So here I want to heat water from 25.2 to 90.5. I want to know how much energy in kilojoules is it going to take to do that. So I'm not evaporating the water. There's no change in potential energy. I'm just looking at a change in kinetic energy. Right? So that's what specific heat is for. So I'd have to be given the specific heat. That's a relationship. That's the specific heat. So specific heat is just for changes. It's just when the kinetic energy changes. If I also had to evaporate the water or change its potential energy in some way, I would need another relationship to tell me how much energy is associated with that. The specific heat is just for changes in temperature or changes in kinetic energy. So that's what's happening here, though. I'm just increasing the temperature. I'm not changing the state of matter. I'm not breaking or forming attractions. I don't have to worry about the potential energy, just focusing on the kinetic energy. So how much is the kinetic energy changing? Well, the temperature is going from 25 up to 90. So what is the actual change associated with that? Right? Because this degrees Celsius here is representing the change in temperature. So the change in temperature is going to be the final minus the initial, 25.2. So when I subtract, I get 65.3. That's the change, right? So if I want to know how much energy is this absorbing, I don't want to know what the initial temperature was really or what the final temperature was. I want to know what's the change in temperature, because that increase in temperature is what's caused by the change in energy. Those are what's directly related. So if I want to know kilojoules, I might start with the heat capacity, because that has units of joules on top of the fraction. And if I want kilojoules, I know a relationship between a base unit, joules, and a metric prefix, kilo. So I can apply that right away if I want. If I want kilojoules and I want to cancel joules, I know that relationship. It's a metric relationship. Then I still know that I need to cancel the grams in Celsius. So I just plug in to get them canceled. I've got this change in temperature, 65.3 degrees Celsius. So that will cancel my Celsius. And I've also got to cancel grams. So how much water do I have? 255 grams. So now everything cancels except kilojoules. So it should be done. $69.7 kilojoules. Questions about that? So that's because I'm asked for kilojoules, but the specific heat only has joules. So when I plug this relationship in here and I have joules, I just realized that if I want kilo, which is the metric prefix, and I have the base unit, I need that metric relationship. All right, so a not very sophisticated calorimeter that you could use, and that's used in undergraduate labs a lot, is just a coffee cup. And you might stack 2 coffee cups together to get extra insulation. You put a thermometer in there, you've got your calorimeter. So the coffee cup isn't perfect, right? It will, if you have hot coffee in a coffee cup and you let it sit there, even if it's covered, eventually it gets cold, right? But in a short time frame, the amount of heat exchanged between the coffee cup and the surroundings is pretty small. Why is a coffee cup so good at insulating hot liquids? Why is it better than, say, a glass mug or something? So we're talking about like a styrofoam coffee cup. Yeah, so why is it that the styrofoam doesn't conduct heat very well? If I want to conduct heat, what we said for thermal energy transfer is we need collisions, right? So glass is pretty good at transferring collisions, right? If you have your hot liquid in a glass container, the molecules in the hot liquid are moving really fast. They collide with the glass. That causes the glass to start vibrating. And since the atoms in the glass are all connected to one another, those waves of vibration travel quickly through the glass, and then the outside of the glass starts to move fast and it becomes hot. The temperature goes up. So the way styrofoam is designed is it's got little pockets of air throughout it. So air is mostly empty space. You've got a few gas molecules in the air, but it's mostly empty space. So air is not a good conductor of heat. It doesn't conduct collisions very readily. What the best insulator would just be a vacuum. You've got nothing. And if I had my hot liquid and then a vacuum with nothing, and then the outside, there'd be no way for the kinetic energy to transfer, because the hot liquid has to collide with something in the container to transfer that energy to something else. So if you have like a reusable coffee mug that you use, it probably has a layer of air between the inside layer where the liquid is and the outside layer where your hand would touch, because that air is mostly empty space. It's not packed with a lot of molecules, so it takes a long time for the fast-moving molecules of the liquid to collide with the inside of the container, and then to get those collisions transferred to the air and out to the outside of the container. So the styrofoam is good. It's got a lot of air trapped in it, which is mostly empty space, and doesn't allow for very frequent collisions between things, and so the collisions don't really transfer the heat very quickly. But it will over time. So if we want to do this experiment and use this as our calorimeter, it's got to be a fast reaction. So if we do a chemical reaction, so let's say I put HCl and NaOH in my coffee cup, I've got my thermometer in there, that's a fast reaction. So the energy released by that reaction should stay inside the styrofoam for a decent period of time, cause the temperature to go up. And if I can measure how much of a temperature increase I have from wherever the temperature started, I know that the temperature is not going outside the coffee cup. And so what's inside the coffee cup is the solvent. And so the reaction has this energy, it releases the energy into the solvent. The solvent is inside the coffee cup. The coffee cup should insulate that, so all the energy goes into the solvent, the temperature of the solvent goes up. I can measure the change in temperature along with the specific heat of the solvent, just like the problem we just did, and then I know how much energy the reaction is released. Right, so these are measured values experimentally, done using an experiment very similar to this. I measure how much the temperature changes. I know the specific heat of the solvent absorbing that temperature. I can tell how much of an energy change there was from the reaction. So that's delta H for the reaction. I've just measured that. So you can look up delta H for lots of reactions, but you can also measure it if it's a new reaction that you're not really familiar with. So this explains how to use the formulas for that. But we really don't need that. We can set it up as a conversion, and we recognize if the solvent temperature is going up, that's an exothermic reaction. So the reaction should be releasing energy. That's what's causing the temperature of the surrounding solvent to go up. And so that's negative from the reaction's point of view. If the temperature is going down, we know that's endothermic, because the energy from the solvent surrounding is decreasing, it's going into the system and becoming potential energy, so it's not there in the form of kinetic energy in the surroundings anymore. The system is absorbing that energy, causing it to be converted to potential energy, so the temperature goes down, there's less kinetic energy, and that is a positive change in energy for the point of view of the reaction. So conceptually, we can work with these without really even needing the formula. So here's an example. I've got a pellet. I know its mass. It's originally at some temperature. I'm going to drop it into 125 grams of water. That starts at basically room temperature. And I measure the final temperature. I want to know, what is the heat capacity of the pellet? So I need some relationships. What relationships do I have? What relationships do I need? I'm ultimately interested in how many joules per degree Celsius for the pellet. Well, if I look at what I do have an initial temperature for the pellet and a final temperature for the pellet. So I can get the temperature change for the pellet without really even needing any relationships. I can just take the final minus initial. It's 57.1. Negative. How do I figure out how many joules of energy the pellet is transferring to the water? Well, what? Yeah, I would use the information I have about the water, because I know that any energy that the pellet, actually I can probably put this in kilojoules, joules maybe. Any energy that the pellet is releasing must be absorbed by the energy that the water must be absorbed by the water. Right? There's an equal transfer because I can't destroy or create energy, and I'm assuming that I'm doing this inside a calorimeter. So if I can figure this out, I know this relationship. It should be a one-to-one relationship because of the law of conservation of energy. So if I want joules for the pellet, I can start with the heat capacity of the water, which needs to be given. That's 4.184 joules per gram Celsius for the water. So I can put that in here if I want. 4.184 joules absorbed by the water per gram of water per degree Celsius that the water changes. Then I can realize this relationship if I want. For every negative joule that the water for every joule that the water absorbs, the pellet will be releasing that. So they will have opposite signs but equal quantities. Then, so this cancels. Then I just need to cancel these two. So I need to multiply by the grams of water, which is 125 grams. And I need to multiply, I'll just put it here since I am multiplying, doesn't matter whether I put it on the right or the left. I don't need to also multiply by the change in temperature for the water. So the water's change in temperature is 88.4 minus 31, no, the water started at 25. 31.3 minus 25.1. So that's 6.2. So that's 6.2 degrees Celsius for the water. Now that cancels. So I've got the energy. So these negative signs cancel. Negative times a negative equals a positive. So everything cancels except joules of energy the pellet absorbs or releases per degree Celsius change in temperature for the pellet. So I multiply the stuff on top, divide the stuff on the bottom, and I get 56. And I really only have 2 sig figs, so I gotta round that to 57 joules per degree Celsius for the pellet. So that is the heat capacity for that particular pellet. That's the number of joules of energy the pellet must exchange with the surroundings in order for its temperature to change by 1 degree per degree, which is what the question was asking me for. Heat capacity. Questions about that one? Yes. The 6.2 was the change in temperature for the water. So I took the final temperature of the water minus the initial temperature of the water.
So the 4.184 can be given on the card?
Yeah, this is not something you have to memorize. That's a specific heat of water. So if you need the specific heat for whatever solvent and it's given in a question on exam, that would have to be given. So another type of calorimeter, which is a bit more sophisticated, is called a bomb calorimeter. And this is used a lot in the food industry to determine how many calories are actually in food. And so when your body consumes some nutrition, the carbohydrates and fats and proteins that are in there could be used by your body for energy. So what your body would do with those molecules is they would start by breaking the initial bonds that hold those molecules together. Then your body would combine those carbons with oxygens and hydrogens with oxygens to make CO2 and water, right? That's why when you breathe out, your body releases CO2, and that's why you urinate water. Those are waste products. Those are what your body creates in the process of getting energy out of the food, right? So the food molecules are relatively unstable compared to the stability of CO2 and water, right? Because that fuel that you're eating, that food, has relatively unstable bonds. It has the potential to become rearranged to form more stable bonds, and that energy is then used by your body to run the various chemical reactions that your body needs energy for. So if you want to know how much energy is in food, instead of consuming it, you could just burn it. Just burn the food, which is basically the same reaction your body uses. Eventually, in the bomb calorimeter, you burn the food, it gets converted to CO2 and water, which is the same reaction your body converts the food into. So if we convert that food, those molecules, into CO2 and water, and we observe how much energy comes out, we can tell what the energy content of that food was. So a bomb calorimeter can be used for anything, not just for food, but it's used in the food industry to make sure that the labels have the appropriate numbers of calories on them. And so what happens here is we get this calorimeter. It's really well insulated. We have a solvent. We may not have a solvent. We may just have, when the food releases energy, it might just be absorbed by the calorimeter. But if we do that, we need to first calibrate the calorimeter so we know for the calorimeter how much energy is required to cause the calorimeter's temperature to go up by a certain amount. So we can calibrate the calorimeter to determine its heat capacity. Right, so if I have a known reaction that I know releases a certain amount of energy, put that in the calorimeter. I know the reaction's releasing, 5 joules of energy. And then I see how much the inside of the calorimeter's temperature goes up. Then I know, for that calorimeter, how many joules of energy it can absorb per degree temperature increase for it. So I figure that out. So I can do that. Or I can put water in the calorimeter, which has a known specific heat, which also allows me to determine if the water absorbs a certain amount of energy, how much energy was given off by the reaction. So then I burn this food, I observe the temperature of the calorimeter or the water go up, then I know how much energy the food released. So that's how bomb calorimeter works. You can use, in this case, if you know the heat capacity of the calorimeter, which is going to be in joules per degrees Celsius, you multiply that by the temperature change for the calorimeter in degrees Celsius, and you know how many joules the calorimeter absorbed. So then what we just said is, since it's insulated, any energy the calorimeter is absorbing must be the energy that the reaction was releasing. And so if that's burning of food, that's the energy that the food had to begin with. So here's an example that illustrates that. So here we have a chocolate chip cookie. This is the mass of the cookie. We're going to burn it in this bomb calorimeter. It's going to release energy. We know the heat capacity of the calorimeter. And during that combustion, it tells us that the temperature of water inside the calorimeter went up by a total change of 3.9 degrees Celsius. So we want to know, what is the energy content of the cookie? So if you eat a gram of cookie, how much energy does that actually have the potential to give your body? So what we want to look at here is, really, this is a kind of a complicated example, because if we look back at the calorimeter, we said when this reaction occurs and the energy is released, we have water to absorb that energy, but the energy can also escape into the calorimeter, and the calorimeter can also absorb that energy. So if the water is absorbing energy and the calorimeter is absorbing energy, the total amount of energy released by the burning or the reaction is the total energy absorbed by both the water and the calorimeter. Right? So all the energy absorbed has to be equal to all the energy released. So if we find in this reaction that the water is absorbing energy, for the water, the relationship is 4.184 joules of energy absorbed per gram of water per degree Celsius. Look at this example in the textbook real quick. It's not totally clear based on how it's worded. Okay, this example is not quite as complicated as I thought it was. So let's break it down a little bit. We have the water absorbing energy, and that they're treating, in this question, they're treating the water as if it's part of the calorimeter. So we have the heat capacity of the calorimeter. That includes the water. So we really don't need this value, because the water is part of the calorimeter. When they calibrate this calorimeter, they accounted for that in this number. So what that means is, when the reaction releases energy into the water and into the calorimeter, this is the relationship between how much energy the calorimeter and water absorb and how much the temperature of the water goes up. They did that using a calibration. So that's our relationship. 39.97 kilojoules of energy per degrees Celsius for the calorimeter. So if this is the temperature that the calorimeter went up by, we can use that in our relationship to convert that into kilojoules. So if I'm looking for kilojoules of energy released by the cookie, we also realize that since the calorimeter is insulated, all the kilojoules released by the cookie must be equal to the kilojoules absorbed by the calorimeter. Nothing should be escaping. So if we want kilojoules released by the cookie per gram of cookie. Well, we can start with the information given. We could start with, if we want, just putting the grams of cookie on the bottom, because that already gives us the unit we want on the bottom of the fraction. On top, we want information about kilojoules. So I would start with this relationship here that I actually have in kilojoules. So 39.97 kilojoules absorbed by the calorimeter per degree Celsius change for the calorimeter. So I need to cancel this degrees Celsius, so I'll plug this 3.90 in. That's what the actual temperature change is for the calorimeter, so that temperature change for the calorimeter in Celsius should cancel the degrees Celsius units. And then I just have to recognize that for every 1 kilojoule that the calorimeter absorbs, that's 1 kilojoule that the cookie released. Now I've got the units I want, so I would just do 39.97 times 3.9 divided by 7.25. So that's 21.5 kilojoules per gram. Any questions about that? Okay, so that's it for today. Next time we'll finish chapter 10 and just a little bit in chapter 13 that that relates to energy as well. We needed chapter 10 background for. Just to point out, the way I've been solving these is using the conversions. And by this point, hopefully you've done enough conversions, you're comfortable with that. But if you're not, you could solve this problem the same way using this formula. So maybe I'll just show that real quick so you can see that. So the formula tells me that the heat of the reaction is equal to the heat that the calorimeter absorbs. That should be equal to the heat capacity of the calorimeter times the change in temperature for the calorimeter. So if I'm looking for the reaction's release of energy, that would be equal to the heat capacity of the calorimeter, which was given as 39.97 kilojoules per Celsius. Multiply that by the change in temperature for the calorimeter, which was 3.90 degrees Celsius. So multiplying those two together would give me the quantity of energy released. Then if I want that per gram of cookie, I have to divide it by the number of grams of cookies. So I still have to work with the units to an extent. I mean, you don't want to, even if you're using the formula, you don't want to ignore the units, because if you're looking specifically for kilojoules, you have to make sure that you have kilojoules here. Don't just plug in the heat capacity and assume that the units will work out. So I plug in the heat capacity in kilojoules, and I want that per gram of cookie, so I have to divide by the number of grams of cookie anyway, like we did on the next page. Using the formula is not really that different from using the conversion. I still have to focus on the units and make sure that the units work out.